Yeah. So in the last class, we have started velocity and acceleration. We understood some basic vector addition, and after that, we understood by just a single turning pair, if we have a link which is rotating with omega radial velocity, or and r is, let's say, the distance or the length of the link, then velocity at the other end of the, with respect to the fixed end or with respect to the hinge end, will be r omega. And then we understood like how we will be able to draw the velocity diagram in the case of a linkage or mechanism. Then I have given you also in case of slider crank chain how the velocity diagram will look like. Then we understood the basic knowledge about the acceleration, like what are the different types of accelerations we have: tangential and centripetal acceleration. And but whenever we have turn slide pair, one apart from acceleration of slider, one more component of acceleration will come into the picture, which is Corley's component of acceleration. Okay, and we also understood how the direction of Corley's component of acceleration will vary depending on the rotation of the link, okay, depending on omega basically, and the direction of velocity of slider. Okay, so this is for the turn slide pair only. So till this we have studied. Okay, we got one question from Sean: how did you rotate in case 2? So I hope you are talking about the Corley's component of acceleration and this case 2, right? Yes. Okay, so what is the definition, Sean? The Corley's component of the acceleration will get by rotating the velocity vector in the direction of angular velocity by 90 degree. So this is your velocity vector here. Okay, and what is the direction of angular velocity? It's a counterclockwise. Okay, so rotate this velocity vector in counterclockwise direction. That's why this arrow is in downward direction. Are you following? Yeah. Okay, so you have to focus on the omega, whether omega is counterclockwise or clockwise. Okay, I'll give one more example here. Look at this last example, case number 4. Here we have omega in clockwise direction. Okay, just opposite of the case 2 here. Okay, so this is the direction of the velocity of slider. Okay, we are rotating the velocity vector in the direction of angular velocity, and angular velocity's direction is clockwise. That's why I'm rotating this clockwise here. Okay, so that's why if you rotate this velocity vector by 90 degree clockwise, you will get the Corley's component of the acceleration. Okay, here also you have rotated by 90 degree. Okay, this is also 90 degree, but it is counterclockwise. That is the only difference. Yeah. Okay. Yeah. Okay. So I would like to ask some few questions to just make sure your understanding is clear or not. Okay. Suppose this is how, if I give you uh, a linkage or a mechanism. Okay. Suppose this is link number A. Sorry, joint A, B, C, and D. Okay. So we have link AB, BC, CD, and AD. And let's say this is omega 2. Can you try drawing velocity diagram in this case? How the velocity diagram will look like? And can you tell me the velocity? Let's say, what is your guess on velocity of BC? How the expression for velocity of BC will look like, or what will be the value of velocity of BC? So here, just if you are not able to understand from this figure, the line AB and CD are parallel to each other. Okay.
It was in pure trans link C BC
Uh, Pardon,
for
could you please
this.
repeat?
For configuration, link C will be in pure translations.
Translation? What translation?
Pure translation, sir. It was for this configuration.
Okay, so you mean you'll get a just single line.
Yeah.
Yeah. Okay, correct. So in this case, there will not be a like a velocity triangle. Here we'll have just a straight line. Okay, because if you see, link A and D is here itself. Okay, uh, sorry, A and D, because that is fixed. And if you, what will be the direction of velocity of link AB? It will be in this direction, correct? At B point, the velocity at point B will be. I'll just use the red pen to make sure you understand. This is the velocity of B. If you, okay, and what is its value? Omega 2 into AB, correct? So basically, this is your B point. Okay, can you tell me where the C point will come? So where will be the velocity of link BC? It will be perpendicular to this, right? So if I use this logic on this line, somewhere point C will be there. But what is velocity of link CD? That will be perpendicular to this line. So that is possible only when your point B and C will coincide with each other. Okay, or this is the same point. Are you following? So in this case, you will get just a straight line. So I would say velocity of AB will be equal to minus velocity of CD. And in this case, velocity of BC will be 0. Okay, um, because our this is the third link. Okay, suppose it is the first link, second link, third link. Velocity of third link, in other words, you can say as 0, because the ultimate effect of it is like there will not be a you can say relative we can say velocity with respect to the fixed points. Okay, so velocity of B with respect to C will be 0, because ultimately these 2 points are like moving together, B and C. Okay, are you following? CD line, yes, CD line is also there. So that's why I told, right? Velocity of AB is equal to velocity of CD. So it means AB is in this direction and CD is opposite to that direction, like this, on top of that. Okay, is it clear? This equation number is clear or not? If you have any doubt, let me know at this moment itself. Okay. So what we understood from this is, whenever two links are parallel to each other, then if we have one link in between them, then the velocity of that link will be 0, and ultimately we'll not get a velocity triangle, we'll get a velocity diagram will be a straight line. Okay, so this is what we understood. Yes.
B and C will be moving in the same direction, so the relative velocity at same speed, so the relative velocity will be 0.
Yeah. So basically, see, what is velocity of AB? Velocity of AB means velocity of point B with respect to A, right? That is what we have studied in the last class. I have given you in, these 2 points. This was your A point and this is B point, for example. Okay, so I told that this or velocity of B with respect to A, if we say like this, or velocity of point B, we can say that means we are calculating it with respect to A. This distance we are considering and omega we are considering to calculate it, right? So whenever we are saying uh, uh, whenever we are calculating any velocity, for example here, this r omega is with that is the velocity of point A with respect to point O, right? So same thing here, we are calculating the velocity at point C with respect to B. So we can so there is no basically a relative velocity in between them, so that is why we are getting 0 answer. Okay, omega is actually 0 in between B and C. At what omega B is rotating, C is also rotating at the same omega. That is the main thing here to understand. Oh, or even if you assume it as omega 3, for example here this omega 3 or this omega 4, the problem is if you calculate the velocity of point let's say B, or velocity of point C is equal, that is what you can conclude out of it. Okay, so there is no relative velocity in between them, that's why the velocity of third link is 0. Okay, I hope it's clear. Yeah, so if you want, you can write down a note that whenever two links are parallel in a 4-bar chain, the or whenever the input and output links are parallel to each other, the velocity of coupler will be 0, and in that case the velocity diagram will be a single line. Okay, that is what we understood from this particular scenario. Okay, now let me give you one more example. So this we have already studied, right? If you remember in the last class, this is the slider crank mechanism. This is slider crank mechanism. Okay, let's say omega is the RPM in which at which the crank is rotating, and AB is our connecting rod, and the B, we have slider at point B, which is, let's say this is link number 1, 2, 3, and fourth link is slider in this case. Okay, so we have studied this situation. I would like to just introduce one more case of this same mechanism. What will happen in this case? So if your crank and connecting rod is, let's say, in a single straight line, in that situation, so this is your link 1, 2, 3, and 4. Can you try to draw the velocity diagram in this case? Try drawing velocity diagram in this case. I'll wait for 1 minute.
Sir,
Yeah,
angular velocity direction.
take any direction randomly. Let's say, for example, if you take this direction, okay, so uh, take this direction. No problem. Okay, take any direction.
Getting right angle triangle, sir. Is it correct?
No, you should not get right angle triangle. Here also, it's like two links are parallel to each other, right? So, for example, this is, let's call these points are maybe A point, B point, uh, C point, okay, and let's call this as a D point. So, same figure I have drawn, just this is um, a different version of it, okay. Almost figure is same, but here we have theta angle, here theta equal to 0, you can say. So your fixed point is point number A, and D is fixed, okay, or you can call it as G generally, because G for ground. And then velocity of link AB will be upward direction, right? Here you will get point B. So at this location, what will be the velocity? What will be the uh, you can say velocity of point C with respect to B? If you practically think here, you will understand this is the extreme position of the slider. Slider will cannot move in right hand side direction after this. This is the end, right? So that's why velocity of slider at this at this location, or velocity of you can say um, BC will be 0. Do you agree? Okay, and that's why this point C will coincide on point A itself, and then velocity of C with respect to A with respect to G will be again this, okay. So here velocity of slider, you can say, is 0, because if you remember, like top dead center and bottom dead centers of IC engine, what is top dead center? That is the maximum height the piston can go, and piston will not be able to move above that, right? So similarly here, this is the one end of the piston, and piston will not move after this, okay. So that's why velocity of slider is 0 in this case. Okay, I hope you are getting these things. Okay, we got one question from Shruti. Sir, what I do not understand is both cranks and connecting rod will at same point come in line with each other. So how can we tell them apart? I didn't get your question, Shruti. So I'll try to explain you about this figure. So if you are rotating this crank in, for example, a clockwise direction, what will happen? This point is after some time will come here, right? And this slider will move to somewhere this location, right? So this is how I'll use red pen to show you. Okay, so if you rotate to here and B will come here, so that is what I am trying to draw here. So this figure will indicate that situation. Okay, so this is the situation where theta equal to 0 and our slider has reached the extreme right hand side. This is the, let's say, dead center, extreme right dead center. Okay, so this is the situation I have drawn in this example. Okay, good. Now you can clearly understand from this is like the point C is reached, the point C here. Okay, or in this case I will write the stuff according to this figure itself to make you more and feel comfortable. This point is B and this was G. Okay, so this is O and G. Let's call it as O and G, and let's call this as E and B. Okay, now is it clear? O to A, velocity of O to A will be in this direction. Okay, and that is what I have drawn in the velocity diagram. And the velocity of link AB will be 0 in this case, because this is the extreme edge. Okay, or this is the extreme end. The slider can go. Yeah, slider will not be able to move after that. Okay, and that's why it's 0. And then we have velocity of BG here, which I have drawn. Okay, so okay, or let just a minute. The here the velocity of slider will be 0. Yeah. Yeah, so this point B will come here, actually not there. Okay, that is the correction only. So you can do it like that. Try to understand the thing here. This is your origin point. Okay, so velocity of OA will be in upward direction here as I have drawn, and then velocity of link AB will be in the downward direction, and the velocity of slider will be 0. Okay, so velocity of slider B with respect to G is 0. That's why B and G will coincide here. Okay, so this is the correct way of drawing it. So write down here OGB will be a single point. It means velocity of point B with respect to G is 0. Why? Because the slider has reached the extreme right hand side. Is it clear? Any doubt here? Yeah. Okay, good. So this is what I was trying to explain. Then let me think of any other cases. Okay, so so this is one point you should know. Apart from this, you should know like how the if angles how the angles will vary in actual diagram versus the velocity diagram. Okay, so for example, I'll try to explain you through this angle theta. So what is theta angle? Theta angle is in between crank and the horizontal line. Okay, so if I roughly draw here crank, it will be this, right? This is theta. So this angle is 90 minus theta. That is what you should understand. So this is very, very useful whenever you solve questions. Like if theta is given in the If theta is given in the let's say the mechanism or linkage, then what will be the angle in the velocity diagram that we can judge on that basis. Okay, is it clear? So similarly, let's say this is point B, and the velocity of this point, okay, so is this, and let's say this is point B. So this is our phi they have given. Okay, so this will be your 90 minus phi. Okay, so you understood how I have written it, this 90 minus theta and 90 minus phi. So the way I am writing 90 minus theta, in the same way you will write here 90 minus phi. And then what will be this remaining angle? It is 180 minus 90 minus theta minus 90 minus phi. So it will be theta plus phi. Okay, are you following it? So if angles are given in the mechanism, I hope you will be able to trace them in the velocity diagram and calculate their values in the velocity diagram. Okay. Okay, good. Let me just check if I have any other special things to explain. So from this, can you tell me how this velocity diagram will look if I have this kind of position of slider crank mechanism? Like I want just shape. Okay, don't go into the details much. Like just to understand your knowledge till now, whatever you have understood. So this is our crank. Okay, so let's call it as OA, and this is OAB, and this is G. This is a right angle, 90 degree. If there is a 90-degree angle in the linkage or mechanism, how your velocity diagram will look like? That is the question. Why straight line? So let's take this example. Okay, so this is the omega, for example. So this is your O point, G point, and this is A point. Okay. Um, yeah. Velocity of B with respect to A will be velocity of B with respect to will be on this line, correct? Correct. And where will be the point? You can say B will be there. Can you tell me where B will be there now in this case? Whether it will be on left hand side or right hand side?
It should be away from the hose.
See, okay, I'll repeat. O and G point is fixed. The velocity of link OA will be in right direction. Okay, and that is I already drawn. So we have point O, we have point G, we have point A. Just only one point is remain, that is point B. At this point, can you tell me velocity of slider is 0 or not?
Not, sir.
Not correct. So that's why the point B will not will be in this direction. Okay, will be at this point itself, because there is a velocity of B with respect to G. Okay, so there is a velocity of B with respect to G. It means velocity of slider is non-zero. Are you getting this? So that's why in this case I'll not write this point B on left hand side, because if I write B here, the meaning of this is wrong. That it means that the velocity of G, or velocity of point B with respect to G, is 0, but that is not the case, right? So the point B will come at this point. Are you following, Shruti? The point will not come at left. Do you agree now? Yeah. Okay.
Sir, but B has some relative velocity with respect to A, no, sir. It should be perpendicular, no, sir.
No, at this particular moment, the B will not have any relative uh, velocity with respect to, like, it's kind of like the toggle position, and at this particular moment there will not be velocity in between A and B. If you can try to trace through this figure itself. Okay, so as you move this, for example, let's call this as OA link in this direction, what will happen? As you move this OA link in this direction, this point A will move in this direction. Do you agree?
Yes, sir. Theta
It means,
increases.
yeah, it means velocity, if theta increases, means 90 minus theta will reduce, and it means velocity of BA will go on reducing. Okay, this velocity in between points A and B will go on reduce. So when theta will become 90 degree, at that point it will become 0. Now do you agree?
Yeah. Yes, sir.
Yeah. Yeah. Okay, so that is the point. I explained this figure first, and then this next figure, to make sure you you understand it. Yeah, so we got one more question here from Shruti. Phi is not 90 degree. Yeah, that doesn't matter. What is what is the value of phi? It will vary depending on the situation. Okay, like what is your length of the connecting rod and what is your crank. So uh, this particular angle only depends on theta, not on phi. Okay, this angle here is 90 minus theta. Phi term is not there. So opposite to VBA is the 90 minus theta. So if VBA increases, 90 minus theta has to increase. If VBA is reducing, it means 90 minus theta is reducing. Okay, if 90 minus theta is reducing, means theta is increasing. Okay, and if you increase it to 90 degree, at that point velocity of point B with respect to A will become 0. Okay, so this is one more understanding we got here in slider crank mechanism. If we have let's say a 90 degree angle in between a crank and the horizontal line in, or the motion or axis of slider, then the velocity of coupler or connecting rod in this case is 0. Okay,
Sir, we can got it from the eye center method also, no, sir. For
yeah,
this.
but eye center I have not taught you, right? Eye center will study afterwards. So you know that, but most of our other students don't know eye center. So I was asking on the basis of what I have taught till now.
Yeah, but we, we are sometimes confused, sir, in graph spectral condition.
Okay. You have any doubt in this particular case?
Yeah, yeah. That line. Okay, sir. It was clear, sir. Up to now.
No, if you have any doubt, feel free to ask. Okay. Um, or if you feel later also, if you have any doubt, you can reach out to me, or in the next class also we can discuss. So it's not a problem. Whenever you
Okay.
think that it's things are not clear, if you are not
Okay, sir.
comfortable in class, you can also reach me. Okay, personally.
Okay.
Okay, then let me check if we have any other special situation. Yep. Let me try to create one special situation. Maybe just for your. Okay. Okay, I'm trying to create this. Let's see. This point we have O, A, B, and G, and this is 90 degree. Okay, so this is a 4-bar chain, and in 4-bar chain I am now creating a 90-degree angle in between two links. Can you tell me how the um, velocity diagram will look like? Think on this. Yeah, it's a right angle triangle, correct. So whenever we have a 4-bar chain, so let's take any direction here. Let's say omega. This is your point O, G, link E, OA will be here. AB, B link will be somewhere here, and BG, sorry, from point A, we'll draw a perpendicular, and from point G, we'll draw a perpendicular wherever it meets. This is your point B, and this is your point A. Okay, so this is your 90-degree angle. Okay, so one more point to be noted here, that if we have a 90-degree angle, if or in between the two adjacent links in 4-bar chain, our velocity diagram will be a right angle triangle. Okay, clear? So how I have uh, drawn this velocity diagram, we have point O and G, which is fixed. Velocity of A will be perpendicular to this. I'll use a red pen, and you can clearly see here what I have done. The velocity of BG will be in this direction, so we already shown here, and velocity of link AB will be perpendicular to this, which is also shown here. Okay, so that's how we have uh, got the point B here. Is it clear till this?
Yes, sir.
Yep. Okay. Okay, can I proceed to the next slide? Yeah. Okay. One more situation, special situation I'll take. Um, can you tell me what is this? What is this?
Slotted one.
No, it's a second inversion. Okay. Um, it's a second inversion where crank is fixed, and we have used in Whitworth quick return mechanism. Okay, it's slider crank second inversion. Okay, so in this case, how the velocity diagram will look like? Same thing. Let me just give you omega here, direction of omega.
Sorry, it was perpendicular to
Your voice is cutting in between. Please go on mute. Sorry, your voice is cutting in between. Please go on mute.
BC and AB.
No, it's not right angle triangle. It's not right. It's any random angle. Okay, it's not specifically right angle. So, oh yeah, basically you will get a triangle in this case. I'm not mentioning here that it's a 90 degree. It's any angle. Okay. So, velocity of slider will be. Let's take try to draw it together. So this is our point number A and point number B. Okay, because it's a fixed link. Velocity of BC will be perpendicular to that. Okay, so somewhere here. Okay, this is, let's say, point C here, and then velocity of AD will be perpendicular to this, like this. Okay, so on this line somewhere it will be there. Okay, or and what is the velocity of what will be the velocity of link C with respect to D? It will be in the same direction, right? It will be in the same direction of this. So here is somewhere you will get point D. Correct? Do you agree? So these two lines has to be parallel, right? Because the slider velocity will be in this direction only, either in this direction or on the backward direction, depending on if it is moving in forward or backward direction. Is it clear till this? Are you also getting the same velocity diagram?
Hello, sir.
Yeah.
Like the slider velocity will be always along the link AD, right?
Yeah, slider velocity will be along the line of action. So for example, if you let's say, if you have, let's say, a box, okay, and it is, and you made it slide on a frictionless surface in this direction, the velocity direction will be that only, right? So same thing here, we are making sure that slider is moving on the same line, so the direction of the slider will be in that direction only. Okay,
And the direction of this and the velocity of link AD will be perpendicular to the link, right?
yeah, so that is what I have drawn. So here this is a perpendicular to a link, and this is parallel, like these two lines. Correct. So this is your point A
So
and B, and this is your point D.
uh, so
Correct.
angle CDA is 90 degree, right?
C what?
CDA. Like the slider velocity is along the link, and our link velocity will be perpendicular to the link. That's my.
which link you want here? Can you tell me which specific link you have doubt? So I'll
AD.
write. Let me write here 1, 2, 3, and 4. AD is a fixed link, right? The link number 3 is a slider, and D is like your guideways. Try to understand.
Okay. Okay. Okay.
Um, or or let me just no, not guideways basically. C is on let's say what we can slider, and D is on link. I would write it like this to make it more clear. So yeah, so what I was saying is the sliders C is sliding on link AD, okay, in the same direction, in this direction, okay, in this direction. That's why the link AD direction is parallel. I'm drawing it parallel. Are you following? The direction of the velocity of the slider, this is velocity of slider, okay. D to C in the velocity diagram, D to C in the velocity diagram is velocity of slider, which is parallel to link AD. But the velocity of link AD will not be parallel to link AD. It will be perpendicular to link AD because it's a turning pair. Are you following? CD is a sliding pair, okay, and AD is a turning pair. That's why the velocity of link AD is perpendicular to the link AD.
Okay, sir. Like that, what I got. Like then, what will be the angle with respect to uh, angle between the velocity of slider and the velocity of link? That
Yeah. So
link
you
form.
have to calculate this angle.
Uh, like since I am asking, since this Vs is along the link and the link velocity is perpendicular to that link force, velocity is perpendicular to the link, that angle CDA will become 90 degrees. That's like that.
Uh, See, 90 degree it will become if I give you here 90 degree, right? I'm not mentioning anything here. In the question, I am not mentioning the this angle is 90 or something like that. If I mention, then you give me answer in the 90 degree. Or if I don't, let's say if I say here theta, then it will not be 90 in this case. I'm just trying to explain like how the velocity, how the direction will look like. Okay. Are you getting how this diagram is drawn? Anyone have any doubt here? Don't go into the angle here. I'm not giving here this is 45, this is 90 or anything. I'm trying to uh, explain you how the shape will look like. Is it clear or not? Okay. So there is another simple way to draw the figure. Okay. And that is what I would explain you now. So on this line itself, if you draw a perpendicular to it, okay, so maybe somewhere like this, and till what point you will write? Till point number, let's say this is L2 omega. Let's call it as the omega 2. So L2 omega 2 is the maybe the velocity of this second link, and then you draw one perpendicular to this link. Okay, so this will be the velocity of link AC, and this is your velocity of slider. Okay, that's all. So this L2 omega 2, then your velocity of slider, and this is the velocity of the next link. So which is link number, which is link AD in this case, okay, or L for omega 4. So this is fourth link, so let's call it as L for omega 4. So if you see, compare it, if you compare these two diagrams, they are just same. Just um, are drawn in opposite direction. Okay, but ultimately the angle between the velocity diagrams are same. Okay, so this is very easy way to draw it, because velocity of slider is along the length, along the direction of the slider itself. So velocity of slider is same, just the other two velocities we are drawing on top here. Okay, and you can make conclusions from it. Okay, so if it is now theta, can you tell me where the theta will come in this the velocity diagram? Okay, I'll write some names here. Small a, small, or let's call some other names, x, y, z. Okay, can you tell me which angle will be theta or which angle will be 90 minus theta in this x, y, z triangle? Anyone? So look at this figure, it's very simple. So yeah,
Angle A will be theta, 90 minus theta, right?
which one?
Here, perpendicular. Perpendicular to C will be 90 minus theta.
Perpendicular to C. No, this is 90
The,
degree. This will be theta. Do you agree?
yeah, yes.
Because for this line, this is the perpendicular, and for this line, this is the perpendicular. If angle between two lines is 90 degree theta, angle between their perpendiculars also has to be theta. Correct? Suppose I'll explain you once again. This angle is, for example, theta. Then if I draw a perpendicular to this line and um, let's say perpendicular to this line and perpendicular to this line, this also has to be theta. Correct? If angle between two lines is theta, then angle between their perpendiculars should also be theta. Clear? So that's why I have written it theta. So if you know any other angle, let's say this is maybe this is 90 degree, then other things so you can judge about the other angles easily in this diagram. Okay, or let's say it is 100 theta is known or any other angle is known, then basically you can easily judge the other angles in this um, velocity diagram. Okay, maybe I will I'll draw this figure once again to make it clear. Try to understand. I'll draw a bigger figure. Okay, okay. Sorry, let me draw it a little downside. Okay, so the perpendicular to this, uh, let's take red pen. Okay, and this is the velocity of slider. Okay, here we have slider. This is link 2. This is first link, second link, third link is slider, and fourth link is this. So V3 is velocity of slider. This is L2 omega 2, L4 omega 4. Clear? So if this is theta, this is also theta. So you can easily judge about the other angles. Okay. So for example, if theta is maybe 30 degree, fine. So what will be this angle? This is 30 degree. This is already 90 degree, we know. What about this angle? 90 plus 30 plus, this has to be 60. Do you agree? Yeah. So like this, you can make easy conclusions whenever they ask question on the second inversion of uh, a slider crank chain. I would suggest you use this method. Okay, it will not be a time consuming. If you follow this original method, it will take little time. Okay, bit time consuming. You have to draw parallel lines and then think where is theta, where that theta will look into this diagram. But comparatively, if you choose this method to draw the velocity diagram, you can easily judge what are the angles, what is L2 omega 2, what is L4 omega 4, and you can make conclusions out of it. Okay, so one homework I'll do, you think on it. Okay, this is 90 degree. Okay, and this is, let's say, theta. So judge about the other angles. How the other angles will look. It's the same thing. Nothing is difficult here. Omega 2, link number 1, 2, 3, and 4. Okay, so try to draw this figure on your own. Yeah. Or one more scenario which we can create that will be more interesting is, yeah, this situation rather. Okay, this is better situation. This is not that difficult. We'll draw here itself. Okay, so you'll draw perpendicular to it. You'll draw perpendicular to this link. So this is your L2 omega 2, L4 omega 4, and this is theta. That's all. This is a solution, and this is the velocity of slider. Fine. I want you to work on this example. Okay, this is 90 degree. Try to draw the velocity diagram of this link. Same nomenclature you can use. This is omega 2, link number 1, 2, 3, and 4. Okay, let's call this as A, B, B on slider, C on link, and this point D. Okay, think on this for your homework. Okay, and if you face any difficulty, you can reach out to me. Yeah. Any doubt till this? Is it clear to you all? Will you be able to work on this example? Okay, then can I proceed to the next slide? Yeah, okay, then let's start a new point, instantaneous center. Okay, we have instantaneous center method, which will also help us to calculate the velocities of the link. Okay, so you can use the velocity diagram method easily. You can calculate, and there's also another on top of that, which also you can help. We can use in order to calculate the velocities. Okay, so before we jump into the exact way of calculating the velocity, yes,
that special case we are getting.
Sorry, your voice is breaking a lot in between. Hello, is it breaking for me for or others also? You're finding it difficult to hear. I'm not sure what is your name, but sorry, your
So
voice
it
is
was
breaking. So please type your question because I'm unable to understand your question. Please type. It is your voice is breaking in between. Hello.
yeah. Is it audible, sir? Now,
Yes. I can hear you now.
for that case we get a straight line, sir. Omega 4 becomes the 0 and perpendicular to each other.
Yes. Here we'll get a straight line. Yeah. Maybe you can just send me answer in WhatsApp, and I'll check whether it's correct or not. But it's straight line. That's you're correct.
Okay, sir.
Yeah. Okay. So let's discuss on instantaneous center definition first, and then we will try to understand how this method works. Okay, what is instantaneous center? Instantaneous center is something different than, let's say, um, center of rotation, you can say. Okay, because we the name instantaneous we are using here, it's not the permanent center, it's an instantaneous center. So let's try to understand. The instant center is also called as instantaneous center of a zero velocity. Okay, it means it lies on an imaginary axis of zero velocities about which bodies appears to be rotated at that instant. Okay, so for example, let's try to understand through this figure number A. Okay, so in this figure number A we have two bodies, body P and body Q. Okay, they are having some relative motion in between them. Suppose if I let's say VA is the velocity of link A, fine, and sorry, point velocity of point A, and at point B is let's say VB is the velocity. So VA direction we know. So if I draw perpendicular to this line, okay, this is our perpendicular. Somewhere I would say that um, about some point on this perpendicular line, this particular link is rotating. Okay, similarly, now if I draw perpendicular to B point, okay, perpendicular to VB, I would say that link is rotating it looks like the link is rotating about some point on this line, and whenever, let's say, these 2 points will meet each other, I would say at this particular instant, when velocity of A is in this direction, velocity of B is in this direction, then this particular point I is the instantaneous center of rotation of that link P. Okay, are you following? Okay, so what I'm saying is we have two bodies. Body is P and Q, and at this particular instant the linear velocity of point A and B are suppose given by V and VB. Then if I draw the perpendicular to it, wherever they cut each other, let's call that point as I, then we can say that I will be an instantaneous center of velocity um, for the rotation of body P. Do you agree? So we can say body P will be rotating about I at that particular instant. In the second figure, figure number B, we can clearly see velocity at point A and B, okay, is in the same direction. It's parallel actually. These two velocities are parallel. Hence their perpendiculars are also parallel. They will never meet. So we will say they will meet at infinity. Okay. So we'll say their instantaneous center will lie at infinity. Correct. It means that this body P is rotating about an circle with a radius infinity. Do you agree? So it's like this body is rotating at some radius here, this r. Okay, this is a radius of rotation, but here it will be an infinite radius of rotation, right? Because our eye center itself is at infinity. So from this I can conclude that basically the point A and B have the same direction of velocity. Their eye center meets at infinity. So the the body P is actually sliding. Okay, it's not turning. It is having a linear motion with respect to body Q. Is it clear now? Okay, these 2 points. Are you following the difference between the case A and case 2? Yeah. If you have any doubt, feel free to ask. So at this particular, let's say instantaneous center is this at this location I, at some different instant, because if I change the directions, let's say if I change the directions, ultimately their perpendiculars will change and their instantaneous center of rotation will also change. So that's why the name instantaneous is added, because the center of rotation is changing at every instant. Okay, so that's why instantaneous center is given. The name is given as instantaneous. We can also call it as eye center. Okay, we can also call it as a eye center. Fine. Okay, so draw these figures. I'll wait for 1 or 2 more minutes. I'll just drink water and then we'll continue. Okay, just give me 2 minutes. Okay, the next point is how many instantaneous centers will be there in a mechanism or linkage, let's say. Okay. Write down this formula. Suppose there are small n number of links are there in a linkage or a mechanism. Then n into n minus 1 divided by 2 will be the total number of eye centers in the mechanism. Okay. Okay. Yeah. Can I proceed to the next slide? One more point I would like to introduce here before we jump into how exactly this method helps us to calculate the velocity. Let's try to understand this one more theorem, Kennedy's theorem. Okay. So consider here three bodies: body P, body Q, and body R. Okay. Let's say body R is fixed for an instant, and body P and Q are rotating about I centers here, PR and QR. Okay, so with respect to R, PR is the I center for body P, and with respect to R, QR is an I center for body Q. Okay, so and let's say P and Q are moving relative to a fixed link R here, and let's say a point PQ. There will be some instantaneous center in between link P and Q also, right? Here we have three links. One instantaneous center of rotation we have in an instantaneous center of rotation in between link P and R. We have an instantaneous center of rotation in between Q and R. So similarly, we'll have an instantaneous center of rotation in between P and Q, because P and Q are moving related to link R. Okay, so PQ is the, you can say, instantaneous center for the bodies P and Q. Okay, so you can say it's the instantaneous center of rotation of body P with respect to Q, or instantaneous center of rotation of Q with respect to P. So anything you can phrase out of these two. Okay, so now what this Kennedy's theorem says, try to think, if I assume that this point PQ is on link P for an instant, then this is, let's say, the velocity of P. Okay, because at that particular instant, the line joining PR and PQ is dotted line, and perpendicular to that is VP. Similarly, how I got VQ, I have drawn a perpendicular to a line joining PQ and QR. So ultimately what we are getting here is we are getting two different directions for a single point PQ. Okay, so what we are getting two different velocity direction for I center PQ in the different direction, which is impossible, right? Because if we have let's say a particular point, that point either will, or each point will have a unit direction of rotation, correct? So it is not possible that that point will move in two different directions. Okay, so this is wrong actually. So what Kennedy's theorem says, that if three instantaneous centers shared by three rigid bodies in relative motion with each other, okay, then I think some words are missing here. Then all I centers, okay, then all I centers lie on the straight line itself. Okay, so the meaning of that is the PQ has to be on line joining PR and QR. Okay, Are you following? If three plane bodies have relative motion among themselves, their eye center must lie on the straight line joining PR and QR. Okay, so PQ are the three bodies. PR is the eye center for link PNR, QR is the eye center for link QNR. Then the eye center for PQ has to be on line PR, has to be on this line itself, PR QR line, because in that case only we'll have a unique straight line VP and VQ. Okay, the direction of VP and VQ will be same. I hope it is clear to you. Okay, I'll repeat the theorem. If three bodies have relative motion among themselves, their eye center must lie on a straight line. Okay, this is the theorem. If three bodies have relative motion among themselves, their eye center must lie on a straight line. It's called as Kennedy's theorem. So we'll try to see now how you will locate the eye center in a 4-bar chain and a slider gang mechanism. Can I proceed to the next slide? Yeah. So in this particular example, this is a 4-bar chain. We have 4 links. Can you tell me how many number of eye centers are possible? Yeah. So basically, in this case, we have 6 eye center. Why? Formula is n into n minus 1, n into n minus 1 divided by 2. N is basically in this case is 4 links. It's a 4-bar chain into 4 minus 1 divided by 2. So 2 and 2 into 3 is 6. Okay, this is how we got 6 eye centers. Fine. So in this case, basically this is how our diagram is. We have okay, A, B, C, and D. Okay, this is link number 1, 2, 3, and 4. Now we already have some eye centers located here. So this 2, which is eye center 1 and 2. So this is eye center 1, 2. What does it mean? It means it is a center of location, or it is a basically the point about which link 2 is rotating with respect to link 1. What is the meaning of I12? It is a center of rotation or instantaneous center of rotation of link 2 with respect to link 1. Okay, so it means it is the center point about which second link is rotating with respect to link 1. I hope you are getting it. So similarly, 1, 4 is one more we have here. Okay, it means it's I14. You can say it as instantaneous center of fourth link with respect to the first link. Okay, so this I12 and I14 are called as fixed eye centers. Why it is fixed? Because that link itself is fixed. Link 1 is fixed, hence we are calling it as a fixed eye center. So I hope you understood about these 2 eye centers. Out of 6 we have studied till now, we have studied 2. Okay, what are the remaining 6 eye centers? we have link 2 and 3 connecting here, and we have 3 and 4 link connecting here. So at this particular instant, the link 2 is rotating with respect to link 3 about this point. Okay, so that point B is basically the instantaneous center of rotation of link 3 with respect to 2. Do you agree? So this 2 3 I23 will be, and the third instantaneous center, and similarly I34 will be the fourth instantaneous center. I23 and I34 positions will change slightly, okay, but their names will not change, right? It's like at this particular moment it is here. If this crank comes down, it will be here, okay, and so basically their location will change. So they are not fixed eye center, but they are permanent eye centers. So eye center 2 3 and 3 4 are called as permanent eye centers. Okay, so what are the fixed eye centers here? 1 2 and 1 4 are the fixed eye centers. What are the permanent eye centers? 2 3 and 3 4 eye centers. What are the remaining eye centers? The remaining eye center is 1 3 and 2 4. Okay, the remaining eye centers are 1 3. So we have link 1 2 3 and 4. Okay, so we have 1 to 2 eye center, 1 to 4 eye center as well. So only 1 to 3 eye center is remaining, right? The eye center in between link 1 and 3. Similarly, you have 2 3 eye center and 1 2 eye center, but 2 to 4 eye center is not there in this diagram. So we have to create these two new eye centers, that is in between link 1 and 2, sorry, in between link 1 and 3, and in between link 2 and 4. Okay, so this is link number 1 and this is link number 3. So the points which are if you like, so basically if you join 1 2 and 2 3, okay, you will get 1 3 eye center. Similarly, if you join 1 4 and 3 4 eye center, sorry, yeah, 3 4 eye center, these two lines wherever cross each other, basically, okay, you will end up with a 1 3 eye center. Try to understand. So these two lines, this is first line I'm talking about, okay, and this is the second line I'm talking about. So whenever they cross each other, this particular eye center is I13. In the same way, whenever we want to get the eye center 2 4, this is the link number 2 and this is link number 2 4. So basically the 2 4 eye center will will get created after joining these two lines. Okay, it's just extending line. Wherever it cuts, that particular point is your instantaneous center of rotation of link 2 and 4. The meaning of this is both link 2 and 4 are supposed to be rotated or are assumed to be rotated at this particular instant about this center of rotation. Okay, in the same way, the meaning of I13 is that the links 1 and 3, or this entire link which I have drawn in the red color, okay, this entire link here, okay, 1 and 3 is part of this link, is rotated about the instantaneous center I13. Are you following it? Okay, if you have any doubt, do not hesitate to ask. Okay, draw these figures. Yeah, I'll wait. I'll just rub the things which are not necessary. If you just draw the figure, that's enough. And you should know this fixed eye center, permanent eye centers. So can you tell me how this 2,4 eye center is calculated? It's based on the Kennedy's theorem. What Kennedy's theorem says? Kennedy's theorem says that if two eye centers or if three bodies have relative motion among themselves, then eye center must be on a straight line. Okay, so that's why basically this is 2 3 and this is 3 4. So we are talking about body number 2, body number 3, and body number 4. So if 2 3 is and 3 4 on this line, then 2 4 also has to be on this line. Try to understand what I'm saying. Whenever I say 2 3 eye center and 3 4 eye center, it means we are talking about three bodies, body number 2, 3, and 4. And according to Kennedy's theorem, if two eye centers are there, then the third eye center will be on the same straight line if they have relative motion among themselves. Okay, that is the reason we are extending these lines. Okay, the reason behind extending this line is this Kennedy's theorem itself. I hope you are trying to relate the Kennedy's theorem here. Similarly, the eye center 1 2 and 1 4 is here. Okay, so we are talking about body number 1 2 and 4. Then the 2 4 eye center has to be on the same line. That's why we have extended this line also. Okay, and wherever it cuts, we have chosen that as eye center 2 3. It means this whole body is supposed to be rotated about this eye center. Yes, Kennedy's theorem, correct. Now write down this fixed eye center, permanent eye center. So these two, 1 3 and 2 4, these are neither fixed nor permanent. Okay, so you cannot easily calculate them by inspection. Okay, you have to locate them by drawing the straight lines using Kennedy's theorem. So can be located using Kennedy's theorem. Is it clear till this? So what is velocity of link 2 4? Is it okay if I say it is omega 2 into 2 4 minus 1 or 2 4 to 1 2 distance? This distance, okay, 2 4 to 1 2 distance into omega 2, because this link 2 rotates at with a velocity omega 2. So I can, so this particular link rotate with omega 2 and this link rotate, let's say, with omega 4. So can I write it like this? Velocity of 2 4, either I can write it as v omega 2 times 2 4 to 1 2 distance, or omega 4 times 2 4 to 1 4 distance. Okay, can I write it like this? So in the other way, I can write now omega 4 by omega 2 will be equal to 24 to 12 distance divided by 24 to 14 distance. Okay, this also you can conclude out of it. What about the velocity of 1,3? Can you tell me velocity of 1,3? Can anyone tell me the velocity of 1,3? Okay, for your understanding, I'll draw the figure. Velocity of 1,3. Okay, try to think. 132. Oh, can I write it as omega 3 times 132 23 distance? Yes, correct. Correct, Sean. Omega 3 times 132 32 distance. Okay, so I hope you understood. Like this way, we can still use the we can still use the eye-center method to calculate different velocities. Okay. Okay, so we got one question from Shruti. Why not 132 34? We are considering omega 3, Shruti. Okay, omega 3 is velocity of 3 with respect to 2. Okay, so um, or let's say it's a velocity of it's omega what I would say, yeah, it's a velocity of link 3 with respect to 2, you can say. We are not
Sir,
using
instead
3.
of 3 4, you are writing 2 3, sir. It was velocity of point C, no, sir. You are writing.
No, I am not writing point C here. I'm writing about the velocity of 1 3 I'm writing. Okay, and the question Shruti is asking is why I have taken this distance and not this distance. That is what my understanding is. Okay, so I would say yeah, I think you are correct, Shruti. Yeah, it's 3 4 has to be considered here, and if we consider it here as omega 2, in that case, I think we should write it as 13223. Yeah. Yes. I hope. Yeah. It's correct now. Okay. Yeah. One three two two three times omega. Just a minute. Let me
Sir,
think on it.
it was omega 4 times I 1 4 to I 3 4, sir. For
Just a
point
minute.
C, if you are writing.
No, I'm not writing for point C. I'm talking about this point 1, 3. We are calculating the velocity of point C.
Point C with respect to 1 3 and 1 4, Nasir. Common center was 3 4.
Yeah. Just
Then
a
it
minute.
would be.
Yeah. So it will be. Let me just check. Yeah. So in the same way, we will do as we have done here. Yeah, it's link number 3. Yeah. So basically, link number 3, you have to use omega 3 times 132 2 3. Okay, why not 3 4? Just a minute. 132. I'll write here 12213. Yes, 132 12. Yeah. So our link 1 is fixed. Try to understand situation here. Here what we have done is we have written omega 2 and omega 4. Why? Because the second link is also turning and link 4 is also turning. In this case, if you see, our link number 1 is not turning, so I cannot write in terms of omega 1 here. The choices which we have are like with writing with omega 3 and 2. Okay. So using that, I am writing this as omega 2 times 1 2 to 1 3 distance. Okay. And with respect to omega 3, if you want, it should be yeah 1 3 to 2 3, I think. uh, yeah, it should be 1 3 to 2 3 only. Okay. And if you want with respect to omega 4, then it will be 1 3 to 3 4, we can say. I hope it's clear now. Shruti, is it clear now when to choose? Not this. Mm, yeah, 1 4 you will choose, not 3. So yeah, I hope you are still having doubt with this with omega 3. Let me also get. I'll come back to you on this why it is 232 1 3 to 2 3. Okay, but this is for sure is correct. As if now you can just focus on this. Okay. Have you written this? Okay, then I'll take one more example of slider crank chain. There also I'll explain how the instantaneous centers are calculated. Okay, let me go to the next slide. Yeah, here I have just taken a random example. Here also you will have 6 eye centers. Okay, which are the 6 eye centers you have? This 1 2 2 3 3 4. 1 2 is in between the fix and crank. 2 3 is in between crank and connecting rod. 3 4 is in between connecting rod and um, the piston or slider, and in between 4 to 1 you can clearly see there is a sliding motion, so their eye center will be at infinity. Okay, can you relate this with the first example which I have given, this example, when we have eye center at infinity? So whenever a body is purely sliding on the second body, the eye center lies on infinity, right? This is what we have understood. So same approach I'm applying here. 1 2 is at the joint, 2 3 is also joint, 3 4 is also joint, but 1 4 will be at infinity. Is it clear till this? So have you understood these eye centers 1 2 2 3 3 4 and 1 4? Yeah. Then which one are remained? The remained ones are 1 3 and 2 4. Okay, so same thing, same approach you will follow here. In between link 1 and 3 you have 1 3 eye centers, so these two lines, so in between these two you have 1 3, and in between 2 and 4 you have 2 4 eye center. Okay, so this again 1 3 and 2 3 are can be traced or can be found by using Kennedy's theorem. Okay, I'll explain you once again. Suppose I'm talking about eye center 1 2 and 2 3. It means we are talking about three bodies, body number 1 2 and 3. If 1 2 and 2 3 are on a straight line, then 1 3 will be on the same straight line. Okay, so that's why we are extending this line. In the same way, if 1 4 and 3 4 eye centers we are talking about, then 1 3 eye center will be on the same straight line. So that's why these two lines are joined together in order to get eye center 1 3. Okay, so in the same way you extend other two lines to get 2 4. Is it clear how we have evaluated this eye center 1 3 and 2 4? Any doubt till this? Yep. Okay, now let's try to understand some velocity stuff here. How will you calculate the velocity of 2 4 link? See, we know how to calculate velocities at joints, that we don't have to study because we already studied velocity and acceleration diagram. The point here is about the velocity of the 2 3, how 2 4, sorry, 2 4, how will you calculate? So if I say it has a 1 2 distance to 2 4 distance times omega 2. Okay, so basically it's just a small link if I understand. Okay, 1 2 to 2 4 distance rotating at omega 2. Okay, what will be the velocity of 2 3 in this case? Can you tell me? It's 1 2 to 2 3 into omega 2, correct? And what will be the velocity of 3 4? Velocity of 3 4 will be 1 3 to 3 4 into omega 3, and that can also be written as velocity of slider. Okay, or let's call it as a v4. Okay. Any doubts till this? Okay. If you have any doubt till this, feel free to ask. Regarding the previous question, calculation of velocity of 1 3, I will explain you in better way in the next class. Okay. If you have any other doubt till this, let me know. Okay, because we are at the end of this um, chapter. Okay. If you have any other doubt, feel free to ask. The new chapter I would like to start in the next class itself. In the next class, we will start gears 10. The dynamic analysis of linkages we'll study at the end. Okay. Okay, then if you don't have any, yes, Sean, you can go through this video, and in case of any doubt, you can reach to me, or you can ask me in the next class. Okay. Shruti, problems we are not yet solving. I am just explaining you the theoretical part. Once we complete the theoretical part, we'll start solving questions. Okay. I'll give you problems on iCenter as well. Okay. Yeah, we'll be having problem solving sessions at the end. If you have any questions on theory part, let me know. Okay, so if we don't have any doubts, we'll end our session here, and we'll continue again in the next class. Tomorrow we'll not be having any class. We'll have, I think, next week directly. So thank you all for joining this class, and let's meet again later. Thank you. Bye. Good night.